Okay, in this section, we want to talk about the relation between strain and displacement gradient. Okay, I want you to know what is the mathematical structure of the string tensor, of the string matrix. See here, begin from the function of deformation. Okay, again, I want to tell you here. This symbol means that a function, okay, we just want to use this symbol to remind you this one is different from this one. And also we can take the gradient, okay, this is called the gradient. This is called the deformation gradient. In the same way, we have the displacement. Okay. Vector. So we can also take the gradient. Okay, because your partial, if you partial x, when x differentiation with respect to x, we get I. This is the identity matrix. Okay. So this is the deformation gradient, and this is the displacement gradient. Called the displacement gradient, which is just okay. And I want to show you how this comes from. U is equal to y minus x again. Again, this one have a vector form, right? It is a vector, don't forget. So it have two components or three components. Depending on which dimension you are working with. If you are working with two-dimensional space, you have two components. If you are working with three-dimensional space, you have three components for this vector. Okay, in this way, we have U1 equal U1 x, right? Equal to U1 x1 x2 x3 U2 equal to U2 okay, I just forgot I had forgotten that I forgot that I'm only working with the two-dimensional space in order to simplify our calculations. So we have these two components like this, and then we take the differentiation and this one can be written as a little bit deformation. A little bit deformation can help us. Okay, so this relation can be expressed in this way. Okay, so because this one times this one plus this one times this one give us this relation. In the same way, we can have dy du2 in the same way, we can write it like this. And this one is the expression, and this one is du, and this one is dx, and eventually we have du partial u partial x dx. This is the concrete expression of the displacement gradient. Okay, with this at hand, we want to show you what is the relation between the displacement gradient and the strain. Here, don't forget. As a result, we calculate the transpose. A matrix can have the transpose. For a transpose, what happened? This one will come to this place, okay? And this one will go to this place. They just exchange their places in the off diagonal term. Okay, this one. Now, this one becomes this one, and this one will go to here. As a result, we have. Okay, and what happened if we added these two terms up? Add them up. Okay, we sum this term with this term, and then we will have what? 2 Oh, as a result, we have 1/2 partial u partial x Okay. See here, it is clear that this is the strength matrix we talked about before. Of course, we can give it a notation like this. Okay? And for the final thing, in my teaching, vector a matrix or a tensor, a 2x2 tensor will have like, we have double tubes, at the bottom of the rotation. Okay, so one tube means that we have one column. We have double tube means that we have two columns. Okay, this is the notation used by some scientists like those professors in Cornell University. And I understand that another notation will go this way. But how about this one? You cannot use as a matrix. It's not very convenient. So in general, sometimes they will have a ball face, very, very thick ball face, black and thick like this. Okay, but it is not very convenient. So since it is not convenient, we use this notation system to express vector and 2x2 matrix. Okay, or 3x4 matrix, just a square matrix. Or yes, square matrix. Yes. Okay, 3x3 or 2x2, up to you. Okay. That's it. Okay, this is the end of this section. Okay, today we want to discuss some idea about the classical strength. The first topic we want to discuss is the directoric strength. The toric strength. Directoric strength. It is a concept about shear deformation. Okay, let me show you one example. What will be the deformation look like in this example? It's simple because there's no shear strength. So-called low shear strength. Right? And we have some normal strength like this. So a material will be deformed into a larger one, okay? Like this. So this is the deformation. Okay, so when epsilon 1, 2 equals 0, you say that there's low shear strength. Okay, but I want to tell you one point you need to know. when absolute 1, 2 equals 0, when the shear component absolute 1, 2 equals 0, because the name of the term, you think that absolute 1, 2 is a shear strain. So now shear strain equals 0. Then the material will have no shear deformation at all. But such kind of concept is wrong. Okay? This is wrong. Because when absolute 1, 2 equals 0, there's still shear deformations. How come? Let me show you. Why? Example 2. I give you another example, and we'll find that this viewpoint is correct. For example, absolute 1, 2 is 0, and then absolute 1, 1 is is 1. Okay, minus 2. Absolute 2, 2 is 2. Okay, it's more easy to illustrate the idea. The strain tensor will look like this. Okay. We have low shear deformation, with low shear strain, and we still have normal. Okay, so what does it look like? For example, we have a we have a material square in square shape, okay, and it will deform. Deformed, okay, into what? Because see here, x11, absolute 1, 1 equal minus means that in the x1 direction it is contract. Okay, in the y direction is extension. Okay, it's extend in the y direction and contract in the x direction. So we will end up with a result like this, approximately. Okay, let me draw it more nicely. Nothing rush. Yes, like this. Okay. A pi, B pi, C pi, D pi. Okay. So see here, we still have shear deformation because if we draw a square inside the body, Okay, and then you will find out that this yellow material, already deformed in this way. Of course, you have a lot of shear because we have 90 degrees of the angle here. But here is not 90 degrees anymore, maybe 150 something, or I don't know, I just, 123, okay, 125, something like this. Here we have 90 degrees, and we have already turned it into what? 38 degrees, something. Not on scale. I just want to give you a rough idea. Okay, not 38 degrees, but a small value of angle. So, see, if you look at the yellow, the white material A, B, C, D, you become A pi, B pi, C pi, D pi. You don't find out easily that the material still have shear deformation. But if you look at the yellow material, you find out that this yellow material have been deformed by a shear deformation. Okay, we can draw it A, B, C, D, E, F, G, H, E, F, G, H, pi, 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 pi. So, okay, so the material, the square shaped material EFGH have been deformed into a thinner material. Okay, of course we have shear inside. We call this kind of shear is pure shear. Okay, so we bring up a term, pure shear, which is different from the term pure shear, simple shear. I think you can look at the book of mechanical material in the undergraduate level. You have studied 2 years ago. And then look at the keyword, pure shear and simple shear. They are two different concepts. Okay, so when f of 1, 2 equals 0, there is still shear. Therefore, Mason inside the material. Okay, so obviously, so the name shear strain is not a very appropriate name for the term simple shear. Okay, means that that is represents only a part of the shear, a part of, but not all of Okay, that is absolute 1, 2 represent only a part of the shear deformation, but not all of. Okay, so when absolute 1, 2 equals 0, you cannot say that there's no shear deformation in the material point. Okay, so obviously when we call absolute 1, 2 is a shear strain, it is inappropriate. Appropriate to what? To call absolute 1, 2 as the shear strain. Okay. So see, understand? Just like if you can beat somebody in Taiwan by table tennis, by tennis, you don't call him the king of tennis. The king of tennis nowadays is Roger Federer or I don't know, maybe Nadal. Definitely not. If you can beat all the guys, then you are the king of the world, king of tennis of the world. If you cannot, you're just a local king. Okay, so in this sense, absolute 1, 2 is just a local king because it can only represent a part of the shear deformation, but not all of the deformation. Okay, so it is not very appropriate to call absolute 1, 2 as the shear strain. Okay, this is the first thing you should be aware of, because in the undergraduate years we had get used to this wrong idea to call absolute 1, 2 as the shear strain. But now, but today you can adjust yourself. Okay, you have a new mind today. And also, I give you one more point. Another way to view this thing. Okay, I give you another way to view this thing. For example, if we consider a material like this, A, B, C, D, deformed by absolute 1, 1 equal minus 2, absolute 2, 2 equal 2, absolute 1, 2 equal 0. And then you can see it very easily. what is the point here? Okay, the point here is you don't, in the old example, we first draw a square material like this, but actually we can just and then cut a diagonal material, a material in the diagonal direction to illustrate our point. But I just want to tell you, you can just take the material in this 45-degree directions at the first step, and then to say that we are talking about a material located like this, and then this material will be deformed by a shear deformation. Okay, like this, because after 1, 2 is minus 2 is subtracted, and then after 2, 2 equal 2 is extended in the in the x2 direction, and after 1, 2 equals 0. And then in this picture, we have 90 degree, and now it is maybe 45 degrees something, I don't know, 125 degrees something like this. Okay, of course we have the shear deformation. It's clear. Okay. If you see, what I want to say is, if you look at the material here, it is 90 degree. So we still have 90 degree here. We still have no shear deformation. Then you are wrong. Understand? Don't put it in this way. This way is a wrong way to illustrate the idea. You see, we have a 90 degree angle here, so we still have 90 degrees. There's no shear deformation. Then you are wrong, completely wrong, because if you this is a one material point. If you draw another material point, you'll find out that there's shear deformation because the angle between two material lines had been changed in this way. Okay, so this is the point I want to tell you, because it is a dangerous idea to think that F12 is the shear strength. Okay, now we have already dequalified the term F12 as the shear strength. It is not qualified anymore. Okay, before we think that F12 is the shear strength. It is disqualified already. Okay, have been disqualified already. Okay, F12 is not shear strength. Why? Because it cannot be it is only a part of the shear strength. It's not of the shear strength. So it is very confusing to use F12 as the shear strength, because when F12 equals 0, there's still some shear deformation. It is misleading to take F12 as a shear strength. Then the next question is, which one, what kind of physical quantity can do the job? I mean, we should define a physical quantity such that when the new shear strength, I don't know what it is now, but this new defined shear strength equals 0, the shear deformation inside the material point is really 0. Okay, and then so F12 is not the shear strength. Then who will be the boss? Okay, or who will be the the appropriate one. Huh? Don't say this. Who will be the boss? Appropriate. What quantity will be the appropriate term to represent, okay, stand for, to represent the wheel shear strength. Okay. Okay. This is the question we propose now, and the answer is easy. Okay. Okay. The answer is easy. It is a very famous quantity in the theory of plasticity. For those guys, they study elasticity. They don't pay too much attention about the real meaning of the shear strength. But for those guys, they study plasticity. It is an important subject to deal with because, as everybody knows, many of the material, when they are for many materials, when they are suffer from plastic strain, or if inside the material there is some plastic strain, then such kind of plastic strain must be induced by shear deformation. It means that if the deformation is a volumetric kind, means that only the volume have been changed, then there is no no plastic deformation. Volume deformation cannot cause plastic deformation in steel and metals. Okay, metals. So in the theory of plasticity, it is very important to understand what kind of quantity to represent the shear strength, because shear strength is the key reason for plastic deformation in metals. Okay, of course nowadays we understand that even volumetric deformation means that the deformation can change the volume of the material, can also induce plastic deformations. Okay, but such kind of details is not the focus here, because we are talking about continuum mechanics. I'm not teaching the course of plasticity now. Okay, so you can study more about this viewpoint in the course of plasticity, but not this course. But I just want to tell you that if you want to find out the answer of this question, you should look at the book of theory of plasticity instead of the book of elasticity. Okay? Plasticity, but not elasticity. Okay, not the subject for elastic material. Okay, answer. deviatoric string, V, toric, deviatoric, deviatoric string. The quantity deviatoric string is the appropriate one to represent real shear. Okay, or all shear. Okay, means that okay. Here we use a stupid word all, because we shouldn't emphasize such kind of thing. But you see, to make our viewpoint clear, I add this this clumsy word here. See, when shear deformation equals 0, no shear deformation, then the deviatoric strength equals 0. When the deviatoric strength equals 0, then low shear deformation equals 0. Okay, but okay, but once again, I must draw your attention that now we are talking about classical string. Okay, the term F12, F12 is the so-called shear string for the classical string. So deviatoric string is also defined for the classical string here. Okay. So of course, deviatoric string can also be defined for large deformations, but this is another subject. Here, the deviatoric string we use is defined for classical string, so we still suffer from the small deformation assumption. Okay, okay. If the deformation is small, then deviatoric string equals 0 is equivalent to all shear deformation equals 0. So deviatoric string is the appropriate term to analyze shear deformation instead of the so-called shear string. Shear string is not an appropriate one. Okay, what is the definition? One, volumetric string, absolute V. Okay, called a volumetric string, absolute V equal 1/2 kk I. Okay, yes. And second, deviatoric string. D. Okay. By this. Okay. By this, we have here means that a classical string can be decomposed into two parts. One part is the volumetric string, which represents the volume. One part is the directorial string, which represents the shear. Okay, volume deformation, shear deformation. Okay, and this is the total deformation. Okay, so we can decompose it into two parts. So see, in this definition, it's clear. If this is the volume change, change of volume. Okay, this term measures the change of volume. You know, when the material become bigger and bigger, okay, then volume is changed. So then this term not equal 0 when the volume change. If there's no volume change, then it is equal 0. F of D is the directorial string. It represents the shape change of shape. Where I put it? Yes. Change of shape. Okay, this change of volume, change of shape. When the shape changes, we have shear deformation. Okay. Let me draw a picture let me look at the time. Let me draw a picture to illustrate this idea. Example 1, example 2, example 3 in this section. What? For example, if you have a material like this, it becomes bigger. Your volumetric string is larger than 0 because what? Because the material become bigger. Become larger. Okay, so we have the volumetric string bigger than 0, larger than 0, but the shape fixed. Okay, doesn't change at all the shape. So since there is no change of shape, the directorial part equals 0. Okay. Example 4. Volume doesn't change. Volume straight, fixed. So in this case, the volumetric strain equals 0. And because the shape has been changed, okay, shape has been changed. So absolute D not equals 0. Okay, the directorial strain not equals 0. Do you understand? Okay, if you understand, then we can continue to discuss another concept. Okay, one more question remains. How or why can we present the volume change? The change of volume, okay? Question answer. Look at the book by yourself. It is a question of undergraduate level. I don't want to waste your time here. You should find out the answer by yourself. Look at the book. Or sometimes they don't call it mechanics of material. They call it the strengths I remember that the book by Timoshenko had this name, strengths of materials. Okay, look at the book and then find the keyword volumetric strain. Then you will find out the answer. Or you can just surf on the web, okay? Turn on the computer, and then you can find the answer easily in the internet, okay? A lot of information in the internet. And okay, and also you can find out such kind of information on your smartphone or your cell phone nowadays. One more question. And okay, I put it as a homework. So you must find out the answer by yourself and then write a small homework and turn it to me in the class. Okay, do it by yourself, and then let's. volumetric string. What is the mathematical expression? Okay, let me write it here. Okay, what it is? This is the identity matrix. And this one is what? Let me tell you. I That's it, very easy. And also we can say that I equal to delta ij. Like this is a conical delta. Okay, and then this one equal 1, this equals 0, this equals 0, this equal 1, this equal 1. So the conical delta have the property that delta ij equal 1 or 0 if I equal j. I not equal j, it is equal 0. We have the basic property of the conical delta. Okay. Now, what is absolute kk? As I had already explained to you, it is an expression in terms of the Einstein notation. What is the Einstein notation? Einstein notation tells us that when an index repeating itself, then we should sum it over. Okay, what do you mean? See here, the index is repeating itself, so we should sum it over. Means that we have sum it from 1 to 3, absolute kk. So as a result, we have absolute 1 1 plus absolute 2 2 plus absolute 3 3 here. This is the meaning of absolute kk. Okay, let us continue for our discussion. Okay, let me write down the whole matrix. Okay. Okay, you understand what I'm doing now, even though it is a little bit ugly. Okay, so we have a 3 by 3 matrix, and then it can represent the volume. So we want to ask this question. Okay, let me show you. The easy way to answer this question is that, see here, this is the total deformation. Okay, and then we subtract from this total deformation the volume. So what remains? What remains is the shear, right? Okay, so we have the shear. This is an easy way to explain this viewpoint, but it is not rigorous. Okay, it is not a very rigorous way. So I want to convince you by more rigorous calculations. By doing this, I first write down the expression of absolute and then minus okay. This is the volumetric strain, and then we replace this by what? Okay, we replace this term by this, and then put these two matrices together to get this. Okay, we put it up together and then do some simple calculations. Okay, we can have such kind of expression now because we put 3 here and 3 minus here, and then we get this, and this one, and this one. And just a easy calculation of what? Junior high school level. Okay, junior high school level, 國中程度了。Okay, we then continue our calculation like this. From here to here. Wait a minute. Wait a minute. Because we have the off diagonal term. Yes. I make a small mistake, and now I correct it here. Okay. Because why? Because we have 0 here, but we have still some off diagonal term. So when we sum it up, we shouldn't put 0 here. Instead, we put some simple shear there. Okay. As a result, so we can decompose this big matrix into 6 matrices. Here become here, here become here, here become here. Okay, and then this part. Okay, simple shears. And then what will we have in the diagonal term? Okay. Yes, we can decompose the diagonal terms into 3 parts. Okay, and these 3 parts represent the pure shear. Okay, this part represents the pure shear. You may ask me how I can do this. Let me show you. This one. Right? We can decompose this term into this term and this term, and take this term here. A, and this term B, A, B, B. This B come here, B. And also we can, in the same way, we can decompose this term as epsilon 2 minus epsilon 3 minus epsilon let me, yes, minus epsilon 1 minus epsilon 2. Yes, exactly. I decompose this term into this term and this term. Okay. Let me check it twice. Yes, I didn't make any mistake now. So we decompose this term into this term and this term and put it as A, B, C, and this as D. Where I put it, C go to here. And where is D? D go to here. Okay. I just do it term by term. And then this one, epsilon 3 minus epsilon 1/3 minus epsilon 3 epsilon 2 minus epsilon 3 third. I decompose this term into this term and this term. And then A, B, C, D, E. Where this term E goes, it goes to here. Where this term F go, F go to here. So in this way, we can decompose the whole directoric strain matrix into the simple shear and pure shear. Understand? As a result, okay. As a result, I decompose the directorial strain matrix into 3 small simple shear matrix and 3 small pure shear matrix. You can see when this equals 0, all the simple shear equals 0, pure shear also equals 0. Okay. As a result, it can really represent all the shear. Okay. It works very well. Have been tested by many material data according to the theory of plasticity. So such kind of idea works very well. Directorial strain is really the appropriate term for the shear deformations, but under the assumption of small deformation. Okay. The final thing I want to explain to you is how. Let me show you. Yes, how this term can represent pure shear load, pure shear. Outlook. What is the outlook of pure shear? When you are pure shear, the outlook is like this. You have 5 and then minus 5, something like this. Then it is pure shear because you have the shear in one direction extend in the two direction, contract on the same amount. Or like this, like this. So when the diagonal term, one is in plus and one is minus, and the absolute value of them are equal, then it is the pure shear. So here, let me show you. I want to tell you the feature of this one. Okay, here. Why this small matrix is pure shear? Because see here, the absolute value, absolute 1, 1 minus absolute 2, 2, absolute 1, 1 minus absolute 2 over 3. So their absolute value are equal. They have equal absolute value, just 5 and 5. But one is plus, one is minus, plus and minus here. Okay? So these two terms have equal absolute value, but different sign. One is plus, one is minus. So it is a typical outlook of pure shear. In the same way, you can see the absolute value of this term equal to this term, even though the sign is different. Okay, they have different sign. One is plus, another one is minus. And this term, the absolute value of this term equal to the absolute value of this term, and they share different sign. Okay, so in this way, I have already given you the viewpoint how the string matrix can be decomposed into the volumetric part and the shear part. The shear part is the directoric string. Okay, and remember after this class, don't tell your friend that absolute 1, 2 is the shear string, or it is wrong. But we are living in the crazy world. So even me, sometimes I just adjust myself to the world I'm living. So sometimes I'm still using the term shear string, because everybody call this term as the shear string. Then I call this as the shear string. Otherwise, just only a few people can understand what you talk about. But most of the world cannot understand what you mean. Okay, it is a very embarrassing situation. So we may still use this term as a shear string, but bear in mind that there is a more appropriate one for the concept. Okay, let me talk about one more topic. Strain induced by rigid body rotation. Let me consider an example. Okay, 180 degree. We have a coordinate, and then, for example, we have a body, yellow body. And then, of course, it is a three-dimensional body. We rotate it 180 degrees, turn it from the front side to the back side, okay? Right side to the left side to the right side. Rotate it 180 degrees. What happened? A material point here, point A, will go to the back of the body, become a prime, like this. So as a result, we have a deformation. y1 minus equal to minus x1, y2, okay, xi. But because we rotated with respect to the x3 axis, so y3 equal to x3. This is the mathematical formula for the rigid body rotation of 180 degrees. Okay, here if you have no problem, then let us calculate the strain, classical strain. Let me calculate epsilon 1,1. Right? But what is U1? U1 by definition is y1 minus x1. This is the deformed coordinate, this is the undeformed coordinate. Undeformed, this is deformed. Okay, this is the undeformed coordinate, deformed coordinate. So their difference is the displacement. Okay, in this example, we know that minus yx1 equals minus x1 to x1. We put it inside this formula. And then turn out with minus 2. But as you know, it tells us that epsilon 1,1 not equals 0. It means that we still have strain. As a result, we understand that the strain not equals 0 which is induced by a rigid body rotation, of course it is wrong. Okay, rigid body rotation should not induce any kind of strain. So this is wrong. W-R-O-N-G. So classical strain is wrong. Okay? This is the viewpoint I want to tell you. The classical strain is not correct if large rotation is involved. So when the and always, not always, very often, when the body is suffer from large deformation, there will be large rotations, large rigid body rotation. So this definition of strain is not appropriate. So this classical strain is not a correct term to represent the real strain in a material point. Because of this, we have the whole semester of theory development to answer this hard challenge. Okay, in the old day, you remember that you can imagine that your scientists find out that this definition is not good for, is not a good way to represent strain. And then they will feel nervous for some time and then find out an appropriate way to talk about strain. Okay, let me continue to discuss the concept related to the classical strain. The title of this section is like this. We had already mentioned two viewpoints. One viewpoint is that the shear strain is not a perfect quantity to represent all the shears. So we should introduce the rhetoric strain. Another viewpoint is the classical strain itself is not an appropriate term to describe general deformations, especially for those deformations which rotate or deform largely. Usually, large deformation often induce large rotation. So the classical strain can only be applied to the situation where the deformation is small enough. Okay, so this is the two viewpoints we had already discussed so far. And in this section, I want to bring up one viewpoint to you. Here, this is the definition of the classical string. And one may ask one question: why we have a 1/2 here? Okay, why not something like 1/3? Is it okay? Or 1? Is it okay? So we can have different choices. Okay. So what will be the reason why we must have a factor 1/2 here? Actually, in the old day, the string is divided by this. Means that in the old day we define a string like this. Okay, but after the development of the theory, it is found that it is better to have a 1/2 here. And now let me explain to you why we have 1/2 here. What is the merit? Okay, this is the indicial form of the classical string, and absolute I equal 1, j equal 1. Okay, so here, if I equal 1, j equal 1, 1, 1, 1, 1, we have this, and then we have this, and then these two and these two can be cancelled out each other. See, especially as we have mentioned before, this term can be illustrated as the classical one-dimensional string. So remember, if we use this if we use the formula like this, gamma ij equal to, then we will have a very weird result, okay? Not very natural. Namely, In the one-dimensional case, we have lambda 1. Then it is inconsistent to the one-dimensional definition of strain. So we should have a 1/2 here. This is the reason why. Okay, it is a easy subject here. The reason is clear. If we have 1/2 here, everything will be perfectly matched. Will be perfectly matched with the one-dimensional theory.